The Philippines is home to more than 100 million people. It is a country susceptible to severe weather. Annually, around 18 to 19 typhoons enter its area of responsibility, with 8 to 9 typhoons making it to land. In addition to this, rain and floods caused by monsoons also pose a threat to the country. Now, with the rise of COVID-19 infections, additional precautions must be made on evacuating people affected by severe weather to avoid the spread of infections in evacuation centers. It is, therefore, needed to have a good grasp on the intensity of these weather disturbances, so a resilient and strategic response in evacuating affected people can be prepared, and to ensure the continuous operations of hospitals and temporary healthcare units. One of the atmospheric parameters that gives hint on the intensity of these weather disturbances is the height of clouds and its changes. This is Ellison Castro, a researcher from the Ground Receiving, Archiving, Science Product Development and Distribution Group of the Stamina for Space Program of the Department of Science and Technology of the Philippines. And I am here to present on how to determine the height of clouds from satellite data. Cloud top height, or the altitude of the highest visible portion of a cloud from the Earth's surface, can be measured in several ways. They can be measured through lasers, through sensors sensitive to the radiation emitted by a cloud, or by capturing stereo images, among others. In this presentation, we shall focus on measuring cloud top heights using stereo images. Stereo images are images of a single location or object captured from different angles. Combining these images will result in a single image giving a perception of depth, similar to how our brains process the images received from both eyes. Satellites using this kind of method to measure cloud top heights usually use at least 2 cameras from at least 2 different satellites, or from a single satellite carrying multiple cameras viewing in different directions. In our case, we will be using a single camera of a microsatellite, Diwata-1. Diwata-1 is the Philippines' first microsatellite and was launched from the ISS on April 27, 2016, in collaboration with the Department of Science and Technology, the University of the Philippines, Hokkaido University, and Tohoku University. It carried 4 optical payloads with varying fields of view and resolution. Diwata-1 was capable of capturing stereo images by using its target pointing mode, which reorients the microsatellite to look at a single location as it moves through its orbit. Each orientation will then have an image of the same location viewed from a different angle. These stereo images are then entered into a software capable of creating a 3D model that shows the different depths of the objects present in the image, which in our case are clouds. Of course, this kind of method has its own limitations, such as the accuracy of the measured cloud top heights. This limitation can be addressed by having a constellation of microsatellites with similar capabilities as Diwata-1. And through this constellation, cloud top heights can be monitored at specific intervals by creating a 3D model from each of the stereo images captured by each microsatellite. In summary, cloud top heights can be measured by microsatellites with similar capabilities as Diwata-1. Monitoring the cloud top heights and its changes can be monitored with a high temporal resolution using a constellation of these microsatellites. Through this method, weather forecasts can be improved and communities can be protected, not just from the impending pandemic, but also from future disasters and crises.